Good evening and welcome to the next installment of Learning from Home. This video will be on rational and irrational numbers. There will be a note set that accompanies this, and I will give you access to the actual PowerPoint that you see me going through in this video. As a reminder, students should be taking notes on all information presented. And before we get going, I just wanted to sort of provide a little forward background information on rational and irrational numbers. So, traditionally, number types are taught with some form of a graphic organizer. This is purely a memorization thing most of the time, and teachers often would just give you a graphic organizer and be like, here, you need to learn how to use this, and remember all of it. I personally don't find that very effective. So I'm going to go about this slightly differently. I am going to provide the graphic organizer, but I'm also going to give you some things that you can use to hopefully memorize these number types a little bit better. So graphic organizers are useful, but they should be used as a resource, not as something to memorize unless you're just that person that is a visual learner and you want to actually memorize it. And if that's the case, then by all means go for it. But I personally have found that it's easier to use memory devices, and all I mean by that is we're going to associate the terms, these definitions, with someone or something to help you remember it. And I'm going to use two techniques as we're going through this. The first is we will relate our number types from most specific to least specific, meaning we will start small and go big. In other words, we're going to start with the simplest of numbers and gradually get more complicated. We will use stories and other associations to remember each number type. Essentially, there's going to be two goals here because there are two question types that could come up related to rational and irrational numbers. The first would be to observe a given number and actually classify it. So I give you a number and I say, hey, what kind of number is this? The second would be you're actually given a problem or you're asked to think about a problem involving a sum or a product, maybe even subtraction. So addition, subtraction, multiplication. And basically it would say, think about what the answer would be, and is that going to be this type of number or this type of number? And that'll make more sense as we go. So the first of the numbers that we're going to talk about are natural numbers. And the easiest way to remember natural numbers is to think, for me, it's natural to count on my fingers. So if you think about the numbers that you can actually count on your fingers, that's like 1, 2, 3, 4, all the way up to, 10. And natural numbers do keep going. I realize that you've only got 10 fingers. But the point is, natural numbers start at 1 and they go into infinity forever. The distinction to make there is that natural numbers have to start at 1. You can't go lower than 1. Whole numbers. So this is where we're getting slightly more advanced. We're adding numbers in now, although technically we're just adding one number. So whole numbers. If you think of the word whole, W-H-O-L-E, just like wholesome, full. If you let it remind you of the other way of spelling whole, H-O-L-E, then you should think, oh, a whole is like something that's empty. And the number that we use to describe things that are empty is 0. And that is the only difference between whole numbers and natural numbers. Natural numbers are, like we said before, 1, 2, 3, 4, and so on. When we extend the definition to include whole numbers, we're just adding 0 in as well. Integers. There's not really a easy way to remember what integers are as far as I know. What I can say is that in most of your math classes, certainly through the latter part of middle school and certainly through high school, your teachers are going to say integer, 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 integer repeatedly. And I think for most people, when I say think of numbers, integers are actually what come to mind. So integers are all the whole numbers that we've already discussed, 0, 1, 2, 3, and so on. But it's also the negative versions of those. So the way I phrased it here is that integers are whole numbers and their opposites. So yes, it's 0, 1, 2, 3, 4, and so on, but it's also -1, -2, -3, -4, and so on. Rational numbers. Easiest way to remember rational numbers is to actually look at the root of rational, which is ratio. Ratio should make you think fraction. And that is typically the distinction that we use when we talk about rational numbers. This is where we start introducing fractions, specifically fractions that have an integer in the numerator and an integer in the denominator. So there are several examples down here. And essentially, if you can make a fraction out of the number, or if the number is already a fraction, and what you see on top is an integer, and what you see on bottom is an integer, it's rational. Most numbers that you have ever worked with up until this point are rational. And I did include that just to clarify, because somebody always points out negative 2's right there, or negative 1's right there. That's not a fraction. True, but it can be written as a fraction. So be careful and make sure you think about that. Negative 2 could be written as negative 2 over 1. That's legal. Nothing wrong with doing that. And negative 2 is an integer. 1 is an integer. So if I take negative 2 and I rewrite it as negative 2 over 1, I've just created this new number that's the exact same number. Only now I wrote it as a fraction, and it fits that definition of rational. Irrational numbers. This is where things get kind of weird. You have been exposed to them before. Easiest way to remember irrational numbers are that, well, they're the things that don't fit the definition of rational. So if you can't make a fraction with the number that has an integer in the numerator, integer in the denominator, then chances are it's irrational. So some examples down here. Notice you do have fractions, like the square root of 2 divided by 2, but the square root of 2 is not an integer. So this first one right here, this negative square root of 2 over 2, that doesn't fit the definition of a rational number because you don't have an integer on top and bottom. If it doesn't fit that definition, well then it's irrational. Same with something like 5 over the square root of 7. Same with the square root of 3. You can't write that as a ratio of two integers, meaning you can't write it as a fraction with an integer on top and an integer on bottom. The irrational number that most of you should be very familiar with or have seen before is pi. Pi is an irrational number. You cannot write pi as a fraction. That is an integer in the numerator and an integer in the denominator. I want to take a moment here, though, and point out that I know for a fact that some math teachers like to give students a shortcut with pi that involves a fraction. And you'll see the fraction 22 over 7, 22 divided by 7. So here's my challenge to you. Get a calculator and enter 22 divided by 7. And once you've got that, look up on the computer pi. Compare the digits you get in the calculator when you do 22 over 7 to what pi actually is. And what you will see is that when you use 22 over 7, it gives you 3.14, which is pi, but the decimals that follow 3.14 don't actually match up. So what 22 over 7 really is an estimate for what pi is. It gets you close to pi, but it's not actually pi. And if you've never heard of 22 over 7 before, maybe disregard everything I just said. Or maybe actually go put it in the calculator and you'll see what I mean, because we're going to talk a lot about elements like that in this course. This idea of estimating and when we use estimation. All right, everything we just talked about are real numbers. So essentially, if we can take the numbers that we're given and we can graph them on a number line, or we can plot them on like an XY plane, think of your X and Y axis, that can also be called a coordinate plane, can also be called a Cartesian plot. If we can plot the numbers on there, they're real. Again, everything we just talked about, all those number types are real. If we can't graph the numbers with our known methods, then that's when we get into the next category, which we don't cover a whole lot in algebra, but you will get into in Algebra 2, which is your imaginary or your non-real numbers. And don't focus so much on this part. It's here purely for information. But I just wanted you to be aware that there are imaginary numbers, and essentially just go try to take the square root of a negative number. You've been told over and over again that you can't take the square root of a negative number, and it turns out actually you can. It's just you can't take the square root of a negative number and actually have a real number that we can work with. You enter this realm of imaginaries, which again, you'll do in Algebra 2. That was a lot. So that's all your definitions. I encourage you to go back through them, think about everything I said, pause the video, rewind the video. Don't just watch it all the way through and think that you're miraculously going to understand everything I just said. All right, moving on. Final comments regarding definitions. So there is a difference between rational and irrational numbers that can be interpreted when you're thinking of decimals. So rational numbers, remember, those are the numbers that we can write as a ratio of two integers. So we can write it as a fraction with an integer on top and an integer on bottom. The nice thing about being able to write a number as an integer on top and an integer on bottom is that if we turn it into a decimal, it's going to be clean, which is to say it's either going to terminate like 1.5 down there in your examples, or 2.32 or 7.5. All of these terminate. Or it'll repeat, but in a predictable pattern. So like, for example, this is kind of, my bad, this is kind of ugly in that the decimal is going on and on and on, but it's repeating 224, 224, 224, etc. So that would also be rational. In contrast, irrational numbers, if you depict them as a decimal, they're not pretty. They do not give you a clean decimal. They will not have any discernible pattern. Pi, for example, is 3.1459265. It never ends. It keeps going and going and going and going. Never ends. There is no pattern. Same with something like the square root of 2. If you actually if you put that in a calculator, it'll give you an estimate. But if you actually try to work out what the square root of 2 is, you will find that you just keep getting a decimal that goes on and on and on. Why is that? Because there is no number that you can multiply by itself to get 2. That's the whole idea of square roots. If you recall, square roots say that if I'm going to take the square root of this number, then there's got to be some number that got multiplied by itself to give me this number. In other words, where you see square root of 2 right there, if this said square root of 4, everything would be great, because the square root of 4 is possible, because 2 times 2 is 4. So the square root of 4 is 2. But that says square root of 2. What is the square root of 2? There is no number that you can multiply by itself to get 2. So what happens, though, is that you can get a decimal. And basically, you just wind up with this long string of numbers that never ends, because it's just trying to get you as close as possible to what that number would be. So essentially what this is telling you is no number times itself gives you 2. But if there was a number that times itself would give you 2, it'd be somewhere around 1.414. Again, somewhere around, not a specific number. So I think the takeaway here should be rational numbers are clean looking. Irrational numbers are messy. All right, here's a graphic organizer. This is traditionally what you'd be given. If you think you can use this to your advantage, go for it. Essentially, each level, as you move from the bottom left corner out to the top right, it adds numbers as you go. But it would help to read that note over there. So numbers in dotted boxes can move up, small to big, but not down. So for example, the number 2 is natural, whole, it's an integer, and it's rational. So to clarify really quick, over here, the number 2 is sitting here in natural numbers, but it's also inside whole numbers. So 2 is natural, it's also whole, it's also an integer because it's inside integers, it's also rational, and it's also real. But notice if you take 2 and you start moving out and you try to go over here to irrational, you hit a wall. Well, that's because 2 is not irrational. 2 is everything else that's here, but it's not irrational. Now, in contrast, you could think of negative 2. Negative 2 is parked out here. Okay, so it's an integer, but you can't go from something that's out here back down. So negative 2 is not a whole number. Negative 2 is not a natural number. Negative 2 is an integer, it's rational, and it's real. Similarly, everything in here is a real number, which means even these irrationals fall into this big, giant, gray, dark gray box that are real numbers. Hopefully that kind of makes some sense. If it doesn't, rewind what I just said and think about it some more. Basically, if you get a number and you are asked to classify it, sometimes it's going to have more than one term that works, particularly the further you go towards natural numbers. If I give you a number down here in natural numbers, then it's natural, it's whole, it's an integer, it's rational, it's all these things. But if you get a number that's further out, getting more and more broad using this graphic, then it's not going to have as many things that describe it. So for example, 2/3 here is rational, but 2/3 is not an integer. 2/3 is not a whole number. 2/3 is not natural. Okay, hopefully that makes some sense. So some quick examples. Classify the following numbers as natural, whole, integers, rational, irrational. Some numbers will have multiple classifications. Okay. Essentially, you look at what you're given, and you either think of your definitions, or you think of that graphic organizer. Right now, I'm going to run through them, and I'm just going to tell you kind of what's going through my head. So right there, I see square root of 5. Already, that's a weird number, because square root of 5 cannot be simplified. There is no number that times itself gives me 5. So already, we got red flags going on here, because that is not going to be a pretty number. So already I'm thinking to myself, all right, if I think about my graphic organizer, if I think about everything we talked about, the nice numbers are over in rational. The ugly numbers, if you will, like pi, for example, and the square root of 2 that we already talked about, are over in irrational land. Well, square root of 5 is also over in that same place. Why? Because if you take the square root of 5, you cannot make it fit the other definitions. So like square root of 5, can you make it into a fraction? Sure. But the square root of 5 is not an integer, so it doesn't fit the definition to be rational. Another way of thinking about that, if you take the square root of 5 and you turn it into a decimal, it's going to be a decimal that never ends and never repeats, which means it's irrational. -2, a little easier to think about. And in my brain, I'm going, well, it's not natural because it's not a counting number. If I'm a baby, I don't learn my negative numbers first. I learn 1, 2, 3, 4. It's not a whole number because whole numbers just add 0. Is it an integer? Yeah, because integers are where we introduce negative numbers. Is it more than that? Well, let's see. It could also be rational. If -2 is an integer, if I write -2/1, that's a fraction. Still the same number, but I just made it a ratio of 2 integers. If what I just did confuses you, I technically already showed you this back on the definition slides. Integer, rational. Now, getting a little bit more interesting. Square root of 6/7. Well, it's a fraction. Some people are going to say rational because they see a fraction. And that's wrong, because that's square root of 6, and square root of 6 is not an integer. In order for this to be a rational number, and by the way, why am I jumping to rational? Because I saw a fraction, and ratio is a fraction, and ratio is irrational. So like we've skipped over all these other ones, natural, whole, integers. We're up here at rational. Well, the problem is it doesn't really fit that definition though, because the square root of 6 is not an integer. 7's an integer, square root of 6 is not. So is this a ratio of 2 numbers? Yeah. Is it a ratio of 2 integers? No. So it's not natural, not whole, not an integer, not rational. That leaves irrational. All right, second example, -2/5. A lot of people are going to look at that and think integer, and they would be wrong. The reason why they would say integer is because they see that negative sign, and integers is where we introduce negative numbers. That is true. We do introduce negative numbers when we're talking about integers. The problem is that is a fraction, and it's already simplified as much as it can be. So we have a ratio, a fraction, of 2 integers, 2 and 5, and it's negative, which is okay. My point is, it's a fraction that can't be simplified so that it looks like an integer. In other words, if this was -2/1, okay, that would just be -2, and we'd have an integer. But that's -2/5, which means you can't actually simplify that any. So this is what you've got, which means we're up here looking at rational and irrational. The definition of rational is that it's a ratio of 2 integers. That's a fraction, so it's a ratio. 2's an integer, 5's an integer. Negatives are integers. We got it. It's rational. So in the previous examples, you're literally taking a number and deciding where it fits on that graphic organizer while also thinking about those definitions. Quick aside right here. You need to know those definitions. And this is one of those things I tell people every year, like, I can't teach this. And what I mean by that is either you take it upon yourself to learn the distinctions between these types of numbers, or you don't. The second problem type that you can be presented with. So what we just went through is the first problem type. You're just given a number and you're asked to classify it. The second problem type is basically just an extension. And what will happen is you'll get a problem. It could be a sum or a product, or it could just be like a hypothetical situation. Think about adding two rational numbers. Think about the answer. Now classify the answer. Okay, so example 7. Solve the following problem and classify its solution. Notice we got the same instructions that we did on the other examples, only now we're solving. Square root of 5 times 2. I would expect some people that forget how to multiply their radicals are going to say this is the square root of 10. That would be wrong. The rule is that radicands can be multiplied together and numbers outside of our radicals can be multiplied together. Well, there's no number outside of square root of 5, which means it's understood that there's just like a 1 hanging out there. And there's no radical behind 2. That means you do not multiply 2 and 5. They have to stay apart. However, we can rewrite this with the 2 in front because we read left to right and that's the convention. So you would get 2 square roots of 5. Now, we're not done. You got to classify it. And this is just a nice little explanation for you. So since 2 square root of 5 includes a radical that cannot be simplified, meaning square root of 5 is done. You can't take the square root of 5, so you're stuck with it. We know that 2 square root of 5 does not fit the definitions for most of our number types. In fact, it only fits one definition, irrational. And there's a little note down here that says, if you look at your graphic organizer, you should notice that radicals do not appear until irrational numbers. If you see a radical and it can't be simplified, it's automatically an irrational number. It has to be. If you see a radical and it can be simplified, so like square root of 4, for example, you need to look a little bit closer, because the square root of 4 is 2, which is not an irrational number. Square root of 5 cannot be simplified, so it's irrational. All right, moving on to example 8. Same instructions. Fortunately, we've got some radicals up there on both of our terms. So that means you can actually multiply the 8 and the 2 together because they're both radicands. So 8 times 2 is going to be 16, but we've got that square root to worry about. 7 times 7 is going to be 49. So you should get the square root of 16 over 49. That simplifies, though, because the square root of 16 is a perfect square. Square root of 16 is 4. This isn't actually irrational, which I would expect some people to look at this and go, oh, it's irrational because it's a radical. Yeah, it's a radical, but you got to simplify. And when you try to simplify the square root of 16, you get 4. So actually, you've got 4 over 49, which is a fraction. And when you have a fraction like that, it's automatically rational. Why? Because you have an integer in both the numerator and the denominator. All right, so some general rules for you to remember. The sum of two rational numbers is going to be rational. The product of two rational numbers is going to be rational. Sum is add, product is multiply if you forget. The sum of two irrational numbers could be either or. Could be rational, could be irrational, it depends. The product of two irrational numbers, same story. It depends. 3 and 4 are not telling you that the answer is, it's both of these things. No, it's telling you that it's situational. So you're going to have to pay a little more attention if you've got irrational numbers involved. Because when you've got irrational numbers involved, it depends on whether or not the radicals simplify. If the radicals don't simplify, it stays irrational. If the radicals do simplify, then it could wind up being rational. Now for the U-try, you got 3 problems here. We'll give it a go. And we will go over this in class. If you've got any questions, please let me know. If at any time during this video I seemed a little sarcastic, that is because it's late and I'm tired. But I wanted to get this out for y'all, and I'm basically trying to pep myself up as I go. I promise it's just me attempting to be a little bit humorous, and also me really hitting hard some of the problems that students actually do run into. And it's basically just my way of letting you know it's okay to have those thoughts. It's okay to be wrong. We can all be wrong together. The point here is to do your best, and if you do make a mistake, to learn from it. So, as I always say, if you need me, let me know. Otherwise, take care, everybody.